Hi, this is Jeff Heaton. Okay, so I had a previous video where I showed you how to install PyTorch. Now we're going to actually make use of PyTorch. And I'm going to show you how to translate Tensorflow Keras into PyTorch. Now, most of my videos have been on Keras because I teach a class at Washington University on deep learning, and it's been on Keras since nearly the beginning. I did use TensorFlow directly before that was more integrated in, and probably will remain that course on Keras because it's on the applications of deep neural networks, not so much the theory. So you end up with a bit more code when you're using PyTorch, and we'll take a look at that. So let's go ahead, and I have the examples here, and I have links to these in the description, so you can go right to the code.
To see all my videos about Kaggle, neural networks, and other AI topics, click the subscribe button and the bell next to it and select all to be notified of every new video.
I'm going to try a different format here. I am going to actually take the code for TensorFlow and I am going to transform it into PyTorch. Now I'm going to use a handy sheet of notes that I have here, just mainly because I have not worked with PyTorch nearly as much as I have Keras. So if you disagree with anything that I say, or if you know a better way to do something that I did here, definitely let me know in the comments, because I'm always learning this stuff myself as well. So I thought this format might be cool to let you see as I type it in, so it'll be a little bit longer than the average video. I'll still cut the pauses and stuff, but this is a slightly different format. I'll be actually typing these changes and making the changes as we go through this. So let me know in the comments, what do you think? Do you like this format, or do you like more how I normally do videos where I just show you the code that's completely at the end? This approach is actually a little more work for me, so I don't necessarily care either way, but just curious which format you guys like. Also, if you're interested in seeing more PyTorch from me, I really like things about PyTorch and Keras. So as I go through this, I will tell you the things that annoy me about each. I'll tell you the things that I like about each. And the whole world is not deep learning, so I still use other libraries as well. I mean, I frequently get comments when I do a TensorFlow, but we want to see this other. Well, I do lots of videos on a lot of things. The whole world is not a nail, or I would just need a hammer. So this is the data preparation. So I am going to do a very simple neural network for this one. I am going to do Fisher's iris dataset. This is where we're basically looking at 4 values to determine which of 3 different types of iris this is. This is a simple as dirt dataset. Simple as the dirt that the irises grow in. But the focus of this not is on how to do something really complicated, but how to take Keras code and convert it into PyTorch. So the first big difference that you're going to see here is in this pre-processing, and I'm definitely very much trying to minimize changing as much as possible. So I often try to use the sklearn and things that are agnostic to either TensorFlow or PyTorch. That way, I can switch the code out very easily, because very often I'll take this and I will send it into LightGBM or XGBoost or something like this as well. So I don't want to tie myself to TensorFlow Keras or to PyTorch any more than I need to, because I often get comments, why didn't you use the built-in Keras function to do that? Well, scikit-learn has it, and that works well. But sometimes you do want to build everything in, and we'll see that a lot more when we look at NVIDIA Rapids very soon. So here I am basically using pandas, and I'm reading in the iris dataset. This part here is going to change a fair amount because the X is going to stay the same. So we're just getting these 4 iris values out, but I'm not going to be doing dummy variables. Dummies work by, you have these 3 irises, so 3 irises, so you're going to have 3 columns, and essentially one of those columns goes to 1 for which of the irises it is. The rest are all zeros. In PyTorch, use indexes. So on the surface, that seems quite a bit more efficient because, I mean, sometimes you can have crazy amounts of dummy variables, very sparse. But under the hood, it's sort of working the same way. Now, they're probably doing something to manage the sparsity so that we're not just blowing through the memory. But this is something that is potentially handled a little bit better, I think, in PyTorch. Less coding. Now, one thing about these, I'm trying to use PyTorch sort of the way it's designed to be used and TensorFlow the way it's designed to be used. You can always kind of wrangle the function calls. I could make Keras accept indexes like this, just use an encoder or something similar. Likewise, I could force PyTorch to deal with dummies, but I'm kind of just trying to go with the flow of the recommended way that I saw, at least on the documentation. So I am going to comment out those three, and we're going to put in the PyTorch equivalents. Now we're going to use something from the scikit-learn preprocessing. This will let me do the label encoding. So instead of doing all this, I'm going to do LE equals preprocessing.label encoder. And then we're going to do Y equals label encoder dot fit transform. So we're doing the fit and the transform simultaneously, very common in sklearn, df species. And then we're going to get species equals link encoder dot classes. And label encoder, not link encoder. And let's run this, see if it actually works. And I actually forgot to switch this out to PyTorch. So let me switch to my PyTorch environment. So let's go ahead and run this, see if it works. Ah, good. Yeah, TensorFlow doesn't exist because we are in my Torch environment. You can use both of those simultaneously, but I've not tried that. Let's go ahead and run that. And that works. So let me go ahead and insert a cell below and just show you too what some of this looks like. So species is that. So basically this one's going to be species 0, 1, and 2. Okay, let's go ahead and cut that out. Now this part, this is going to like quadruple in size as a result of switching to PyTorch. Now this is both good and bad. If you're just wanting to get into this and not necessarily learn all of the low levels of neural networks, like maybe you are in an applications class, and I know some of you are saying, heresy, know how this thing works down to first principles. But this does get into a bit more coding. So let me show you this. And I do like how you really do get to see what's going on in the underpinnings in TensorFlow. In PyTorch. So first let's get the imports. Import torch. Torch.nn as nn. Import torch.nn.functional as f, and all of these are needed. Import numpy as np. I might already have numpy, but you can never have too much numpy. From torch.autograd, import variable. From sklearn, import preprocessing. Actually, we already had that one. Now, PyTorch is very object-oriented, and object-oriented is a whole thing. I mean, people in Java go nuts with object-oriented. There's entire books on how to go nuts with object-oriented, and I don't suggest going that far. I found dynamic liberating after being a hardcore OOP guy with Java. But it's not too bad. I mean, you're going to create a class called net, and it's going to extend from module. And we're going to create a constructor. So there's a lot of object-oriented terminology that you have to learn about for this, but it's not too bad. I mean, you don't have to go crazy deep. So you always put self first, and then the input count and the output count. And then we're going to call the base class. So the base class is module. We're going to call the base class and do super net, self. I'm going to have at least a few errors when I try to run this. And dot init. We're literally calling the constructor. Now these input and output, we don't have to pass that into there because the constructor for module takes no parameters, at least none that we need to pass in. And now we're going to do the equivalent of these three layers. We're going to do self.fc1, and the input count on that is going to be incount. This is the input layer to the neural network. And we're going to give it 50. So we're going to 50 input neurons. So that's the 50 of that first hidden layer up there. Then we're going to do self.fc1 equals nn.linear 50, 25. Okay, so that is the 25 there. What is this 50? It's essentially that 50. So that's a little annoying. You have to keep duplicating this, and it just keeps going down. And this is just one more thing to screw up. So if we did 51 here, it's gonna bomb. Whereas here you're adding these in, so essentially Keras already knows that, and it'll just fill in the 50 for you. And that's wrong. That should be 2. FC3, fully connected 3 equals nn.linear 25. Again, 25 from there, comma, output count. And then we're going to do self.softmax equals nn.softmax dimension 1. Because we have one output, which is the species. Really, we have 3, but that's kind of abstracted for you. And then we're going to do def forward. PyTorch really lets you get involved with that whole feed-forward backpropagation neural network. You have a forward function. You also have a backward function. We're not going to redefine backward because the base one is good enough for what I'm doing here. But x is the input that you're providing into the forward layer. And we're going to do we're going to do x equals function.relu self.fc1. We're calling our first fully connected layer that we defined up there, x. Then we're going to call x equals self.fc2x, and then x equals self.fc3x. So you really get to see what's going on with this forward layer where you're going from the input to the output. And then finally, we're going to return. So now we're going to put in the softmax x. So you can see you're really engaged with what's going on in this forward layer. Now, if it's just a simple forward layer like this, where we're just going through the 3 layers, this seems like a lot of extra typing, and who cares? But if your forward layer, if there's a lot more going on in there than the simple case, particularly in research where you're creating structures that are not previously seen before, then I can see why PyTorch is awesome, and I can see why it's taking such a larger role in research currently than it is with Keras. I'll tell you, the other thing I really like about PyTorch 2 is the PyTorch team really gets the releases out and in Conda packages for the various platforms, Windows, Mac, Linux, so that you can get the later versions, whereas usually with Tensorflow, I'm dealing with different versions of it being available for Mac, Windows, and Linux, which is always fun, helping my students being on various different versions of the same thing. So anyway, this is the forward and backward layer. I should be able to run this. This should work, or not. Numpy, not nump. Excellent. Okay, now it's not running any of this code yet, so who knows what could go wrong, but I think that's pretty well correct. So that's my class. Now we're going to get the data into the PyTorch tensors so that it can work with it. xtrain equals variable torch.tensor. I probably could use a float tensor here. I'm going to leave it like I have the example. xtrain, now I convert it to float. It's probably a little more code than I need. xtest equals variable torch.tensor xtest.float, and then ytrain equals variable torch.longTensor ytrain. So these last two, ytest also equals variable. These last two are longs because they're indexes, 0, 1, 2. You don't want decimal places in your class indexes. Okay, so that should work. but does it? Yes. Okay, so that's a good sign. Now let's go ahead and create the model. Thinking I'm doing Java. Net x.shape 1. So that's the shape of x. So how many columns do we have? That's why there's a 1. So 4. I don't want the 150 rows. So that's why we're doing the 1 there. And then we're going to do the length of the species, which comes from up here. And the loss function, which I'm calling the criterion, equals nn.cross entropy loss. So that's your loss function. You're trying to minimize that. And the optimizer, it's your training function. And one thing I do like about PyTorch is those of you that have followed me for a long, long time will remember incog, which is a Java. I mean, I wrote the framework from scratch to do neural networks before deep learning really kind of took off. And this is how I had incog set up very much, because I preferred the lower level. But you're passing in the parameters. These are the weights of the neural network. These are the things that you're seeking to optimize. So we're optimizing the weight to crush that loss function to as close to 0 as we can with a learning rate of 0.01. And now, this is also similar to how I did it with incog, but we don't just call .fit, because .fit makes me nervous anyway. And you can do a step-by-step, epoch-by-epoch call to Keras, but it's not kind of the default operation, whereas in PyTorch, that fit that we had previously in Keras here, this one line becomes about 10 lines. So definitely PyTorch is much more verbose for epoch and range. So it reminds me of cars a bit, how you have your automatic transmissions and manual transmissions. Almost nobody buys or drives a manual transmission anymore. Even me now. I drove one until about a year ago. But I finally gave up and said, okay, it's automatic, especially with self-driving cars for sure, but electric cars, I mean, there's no need for even a transmission, period, let alone one that you have to control yourself. So optimizer, 0 grad. So we're going to 0 the gradients. This is an important step because you need to 0 out those gradients. Those are the errors that you're accumulating as you go backwards through the neural network when you're back propagating. Sometimes, though, you don't want to 0 those if you're doing a more cumulative effect, or you want more control over them. So I've had cases where in Keras where I had to do some low-level stuff to get around and to provide this kind of capabilities. But we're going to do now the output equals model. So this is your forward pass, x train. This is going to call our forward. We're going to get the output. Now this is the output for the entire 150 samples. So there's no batching going on. There's one big batch. So if you wanted many batches, that would be more code still. But loss, this is the difference between the output that we just got and the train, the Y train. And then we're going to call backwards propagation. This is where those gradients get calculated. And then we're going to do, at least I believe, they might actually, pretty sure they're calculated there, but anyway, optimizer, that step. So that gives the optimizer now the chance to use those gradients and to apply them and hopefully decrease the loss function. And then let's print out our results. F string, epoch, interpolate, epoch plus 1, string interpolation. Loss is loss.item. And there we have it. Let's see if that runs. It'd be a miracle. Wow, okay. So you can see the loss starts out, decreases, decreases, the cross entropy slowly goes down. Now we're going to evaluate the accuracy. This mostly stays the same. This is actually one thing I don't like about PyTorch, although it is less typing, which is strange for PyTorch. We don't do .predict. I more prefer doing .predict because that keeps it compatible with sklearn. Because I'm not always using deep learning. I might be using XGBoost or light GBM or something else entirely, like a random forest. But this is how you query it, so that gets you the predictions. Those predictions are probabilities. So if you looked at that prediction array, it'd be all the rows, so 100, well, not 150, it'd be however many are in the test set, because I did split test and train. So train is not a full 150 either, but it's going to get all those rows, but we're going to get those individual predictions. So each row has a prediction, 0, 1, 2, for the 3 different types of iris. We need to call argmax to find out for each of those rows what is the maximum. So for the predicted classes, I am going to basically, I'm going to use torch to do this, just so I don't have to convert back and forth. And the 1 just means that we're doing this per row. We don't want to do it per column. We don't want 4 maximums. We want the maximum for each row. We don't have to determine the expected classes because we're not in dummy variables. And I can then just change this to ytest, and we can call this and see what the prediction is. Yeah, I misaligned something. So this is a common error, actually, that I see students come to me with. And now I've committed it myself. That just means to ignore the first parameter. That I definitely forgot. I don't know if it's the problem or not. Yeah, and that was the problem. So that just, in Python, that's usually a way to throw away one of the parameters or one of the return values and then predict classes. So we're getting 97% accuracy, which is good. Okay, so this is the example. You can see both the TensorFlow before and the PyTorch after code in the description below. Thank you very much for watching this video, and if you're interested in PyTorch, definitely click like, let me know. I follow the likes. If you like Keras, also click the like, I don't know. So subscribe to my channel, and you'll see further videos from me on artificial intelligence, deep learning, and all things AI.